So next, I'm going to show you this code in practice. Okay, so I'm going to go to expense to do this fast, but this I have actually tested on Keynet. The code can run on Keynet also. So here I have prepared the documents on here. We go to the workshop. I'll first show the thermoelasticity. So here, you copy this this environment. This is the environment definition. For example, I create a I create this save. And to install, just here I used let's see, it says microlambda create using this environment file.
You are running?
Hi, I'm installing this package. So it asks me if I want to install, and here I apply the change. This will download the required components.
Hi, can you hear me?
Hi.
You zoom into the terminal. The text is a bit tiny.
Okay, I'll try to. Is this better?
It didn't change.
Yes, that's better.
Yep.
Okay, so command I copy from this page. I guess that page is are available from a group page. So you go from here, the related resources. And there is a CL, and this is thermoelasticity. And it tell you how to install the code. And that is what I'm doing on the machine. Actually, this is going a little slower than I expected. So I have it installed somewhere else.
Can you increase the size of
Yeah.
the font size?
Yeah. Okay, so let me see. So assume you have finished install, then you will be able to use the CIJ command to show you the usage and the available stop commands. So now you can clone this repository. Yeah. Within the repository, yeah, it's here. So we go to CIJ. So CIJ then examples. You can see there are 3 examples: akimotoite, rejuvenite, and diopside. You go to each directory. So there are 3 files. The input 01 is the input 01 is the quasi-harmonic approximation input. Here I can go into that file. You can see at the top you specify here we have 8 volumes and 16 number of Q points. And for each Q points, we have 30 moles. And after that is the pressure, volume, and energy. And after that is the frequencies for this point, for this mode. And after that, you have the second Q points. And the third. And in the end, you will need to specify the weight, the coordinates and the weight of each of these Q points. And the second file is the static elasticity. here you can see we have a bunch of volume, and on the first and second line you specify this is the reference volume, and this is here we have 8 different volumes here, and the mass of the Akimoto cell, Akimoto as crystal. This is 200, and we specify the volume and C11 and to C15, and this is the volume of the first volume, and the corresponding C11, C22, and C33, and so on. And in the end, is the lattice parameters, A, B, and C. And the last file is the settings. So on top, you have the QHA definition. Here you define the delta T and pressure and pressure difference. This is the definition of the PT grid you want as output. And the second part is the elasticity, where you specify input and the settings for the system and the output. So the available input, the available settings can be seen from our paper, which is this one. Or scroll down, and yeah, and here you have a table which specify which settings means what, and the type of the settings. For example, for
Can you please increase the image?
yeah, here is the settings and their what it means, and the available setting. For example, for the elasticity, the crystal system, you can set triclinic, monoclinic, hexagonal, and so on. For interpolation, you can use one of these methods, and how you interpolate this method. And the last section is the QHA. It's the output section where you specify the pressure, the name of the variables, such as Cij, velocities, and Book and shear moduli. Yeah, and these are also have a table showing, for example, the adiabatic elastic moduli, and the unit for this variable, and the convention for the output name. Now I will try to run this code. So Cij, if I just use Cij, it will give you the available output. For thermoelastic coefficient calculation, we need to do a CIJ run. If you just type in CIJ run and help, it will tell you the settings. Here is CIJ run the settings. And here the calculation should be starting. It first tell you on the pressure range you can do the calculation on. And some output. Okay, I actually should use some, yeah, the calculation finished. Now you can see we have a lot of new files ending with txt. Each of this is a table of the variable as a function of pt. I'll go into that. For example, let's go to C11. This is difficult to see. Let me try to show it here. This is Akimoto and C11. So this is a table of on the each row is the row the column title is the pressure. This is 0 gigapascal, 0.5 gigapascal, and so on. And each row is a different temperature. You have 0 Kelvin and 100 Kelvin and to 3000 Kelvin. And these numbers are the C11 at 0 Kelvin and 0 gigapascal, and so on. And we have different variables, and we can extract them to, for example, a table contain these files. Let's say we want if we want this, we want at 300 Kelvin. These variables, it will give you a new table. The new file is this. And if I open that file, refresh. And it's here. So you see this is at 300 Kelvin, you have a different pressure. And this is for the volume and C11 and to C60. And after that, you have the book and share moduli. And so this variable name are specified in the command line. Now we also have a tool to do some static elastic calculation. Here I'm going to show, for example, CIJ run static. And this is the name of the first file and the second file. This is just interpolation of, or processing of this file. I'll write them into output. Yes, so this is the volume free. This will give you the volume. This is the free energy and pressure density and the corresponding component. For example, the CO1 to 666, and it calculates the book and share moduli at this static conditions. So this is an example of doing the thermoelasticity calculation. And next, I will try to show you how to do static elasticity calculation, which is how to prepare for this input file. Okay, this is taking too long today. So here I have prepared an example doing sodium chloride. I will create a new one and copy this. So while copying, I will show you a brief introduction to this workflow. So let me increase. So the structure of this workflow, you will have these three directories on underneath this top folder. As trying to increase this. A directory called scripts, which contains a bunch of scripts which do this transformation of different files. A templates where you put all this template for building the input data, and the workflow folder which contains the for this different workflows. Here we have the convergence test, static elasticity, equation of states, and phone. But I will be just using the equation of states and static elasticity. And on top, I have a summation script and the initial structure and the configuration file. And this is the entry point for the workflow. Our code, my code is built on top of this software called SnakeMake, which use file called snakefile, which contains a Python and a kind of makefile. So in my code, each script defines a transformation of files, and everything is bonded together by this SnakeMake. And the dependency is determined by how you specify the input and output. And in the calculation, what we'll be doing is we first scale the lattice. We have an initial structure. We change the volume a bit, and we will be relaxing the structure. This is actually unnecessary for the sodium chloride system, but might be necessary in more complex systems. And after that, we will be scale the lattice to string the lattice. For example, which I showed you earlier, to apply a 1% stretch in the A direction and compress in the same direction, and do some structure optimization. This reflects the system of the internal degrees of system. For sodium chloride, this also is not necessary. But more importantly, we need to calculate the stress. We have the stress for the plus and minus system. And after that, we will obtain the elastic coefficient C11, C2, C13, to C16 for this E1, the first string. Here now, if everything finished, I can start do some calculation. So if I go to this directory, so here is the top level. You can see there is the scripts and the templates and workflows. Now you need to so to perform the calculation, you need to change. Let's see. So here's the configuration file. Here we I will remove it. Here I specify the system, the number of atoms and number of types. For sodium chloride, we have two files. We have two types of atoms. So here the N type is 2, and the number of atoms here I can show is this. This is the structure for the quantum espresso. And on top, we have the lattice parameters and atomic positions. We have 8 atoms for sodium chloride. So here the definition is like that. And now, if you actually do the calculation, you need to also change. This is the templates for the structure relaxation. To actually run this, you need to change the pseudopotential directory, which I have say in this this directory, there's a README file for static calculation. And here, there is a checklist for which file you need to modify to prepare for the input. But before, you need to download, for example, a pseudopotential from, this is the ultra soft pseudopotentials from this website, and then change this pseudo directory accordingly. And you also need to change the number of this atom definitions, atomic species. The same is for this elasticity input, where in the previous file, it is the VC relax, which you relax both the internal degrees of freedom and the crystal structure, and also the crystal shape. And you also need to take care of the atomic species and so on. So now, I will first prepare to scale the lattice and do the equation of state calculation. Here I specify snake make. Oh, I need to go to an interactive node. Okay, snake make gate. This is to run this code generation workflow in parallel with 8 jobs, eight different jobs in parallel. Actually, I can use more. Okay. Yeah, it's this one. Today the expense is very slow. So this will give you the information of which files are created. Okay, everything. So to do the equation of state, everything is within the relax folder. I'll show this. Let's see. Okay, here shows a structure of this file. So under relax, you have different volumes. The volume equals 110. And you have init.qe. This is the structure of the file. And you have a job submission script, which I will not be using because the calculation is fast here, and the structural relaxation. Then I will show you the contents of these files. So you can see here is the structure for the 110. And you can see the atomic positions will be same as, for example, 120. But only the parameters of this lattice were changed. So and they were changed to make the volume to equals 120, and the unit is extra. The crystals, the crystal coordinates are the same, and this is everything is start from this init from top level. Everything will start from this structure, and it was compressed to this point to make the volume equals 120. And to run this calculation, I will just run dash run in serial. And this will calculate, perform a structure relaxation for each of these volume. And you can see on expense this finish in like a few seconds. So after this calculation finish, you will need to collect the data. And I can first show you the contents after the calculation. So now after the calculation, here we have a folder. We have an output and arrow, and also a script folder. This is the temporary file that is not necessary for the equation of state calculation, but we will be looking at the output, and everything will be collected out of the output. I will show you. So this input, in this input, above this line, above the cell parameters, this was just a copy paste from the templates file, which is from templates relax. You can see in this file, we doesn't have the crystal, the crystal definition, but we have everything else. And the rest of this file is the init.qe. And the second file we want to look at is the output. You can see this is a regular quantum espresso calculation. And it finishes in a few seconds. And what the equation of state calculation will be using the final energy. Oh yeah, here the total energy, this one, and the pressure is obtained from this part. Here we'll say what's the pressure, what is the stress. This is the stress of the diagonal component. Here, because the system is sodium chloride, so there is no relaxation to do, and the diagonal terms are all the same and equals to the pressure, and the off diagonal terms are all zero. Here, the pressure is 212 kilobars. Now I can exit and collect the results using the command. These commands are also specified in this file, which is the equation of states. This will show you which files are processed, the input and output. You see here we collect the pressure, volume, and energy. And now we have this file is contained in this pve.dat, where this is the pressure in kilobar calculated from the quantum espresso output, the volume, and energy. The volume, the unit of the volume is atomic unit, and the energy is a Rydberg. So, and secondly, we have the equation of state parameters. So in this equation of state parameters, where we have this is V naught, the volume at pressure equals 0, and this is the K, which is the compressibility at 0. That's 0 pressure, and the third one is the K prime, which is defined in the equation of states. We can compare. I have listed these numbers here, but we can also compare to the in this repo. I remember there is a table. You can find here. This is the sodium chloride B1 phase, and this result should be same here. So the V naught in our calculation is we have 8 atoms and we need to divide it by 4. So this is almost the same as this one. And 30. And the compressibility at 0 pressure is same as this, LDA. And K prime is about 4.6 and about the same. I have reduced accuracy to make the calculation fast, but this basically demonstrates how you calculate the equation of state. So now I will move on to calculate the elastic coefficients. Go back. Oh, we have also the files that will just show you the equation of state. Let me show here. We now have the relax folder, which contains the equation of state calculation. And this is figure showing the free energy versus volume. This is actually electronic energy versus volume. And secondly is the volume versus P. This is the compression curve. The data points are the calculation and the curve is the fitting. You can see they agree quite well. Next, I will show you the elasticity calculation. So the command to do the elastic calculation are very similar. It's just elastic target. This will build the input for doing the elasticity calculation. So it will take the final output structure from the relaxed structure and the strained lattice to obtain a strained lattice. Let's read this for finish. Then I will show you. So now we have this folder called elasticity. And at this, also at below the elasticity, we have different volume. And here for the cubic crystal, I only calculate E1 and E4. And we have a plus and minus in the strain. Here I strain the lattice by 0.5%. And within the folder, you will have the structure, the input, and the job file. Let me show you the difference between the structure before the string and after the string. So to strain the lattice is pretty easy. I will show you first the crystal structure before the strain. That is this is the structure after the structure relaxation in the previous step. And we use this command and E1, if I remember correctly. This is the amount of strain I want to apply. Okay. And we pipe in the input. And you can see we changed the lattice parameter in the a-axis. We apply 0.005 stretch, and the a-axis is stretched slightly. But the rest of the terms are only very briefly changed. If we times the lattice parameter using this matrix. And this is the structure of this A110 E1. Yes, so this is the same. This we in the workflow. This is the structure of the string structure. Okay. Now I want to do the quantum expressor calculation for this all these string configurations. We do dash. We'll just copy. The run serial will run this calculation in serial, and the submit will submit the job to the job accounting system. And this will also be fast, so I just do calculation. And here, I'm actually doing the same calculations. Let me see if they finish or not on KeyNet. Yes, but it is a little bit slow. It takes like 7 minutes, but I think it's doable. But it just takes too long. I submitted these jobs yesterday. So you can see for each of these calculation, we calculate, for example, volume equals 140. We have E1 and plus and minus the string, and E4 plus minus. And the calculation finish in a few seconds. Okay, the calculation is finished. Right now, I want to process the output of these files. We run this command. This will obtain the elastic coefficient data. Okay, the final output is this file called elasticity data, which is let me see. The line is too long. I will just use the editor. Okay, so this is basically templates for the input 02 I showed you earlier here. Input 02, where you specify, you only need to add the first line where you specify a reference volume and the number of volumes and corresponding mass of the unit cell. This is very similar to this. You will need to remove this column from pressure. And this is the lattice. This is the lattice parameters. Yeah, and you can see because we only apply the E1 string and E4 string, we only have C11 and C12, but the rest of term, we can use our thermoelastic coefficient code here. We have a utility called CIG fuel. which you can specify a system. This will fill this 0 terms for you. So you won't have to do the calculation here, just to make the calculation faster. And so the process of solving for this elastic coefficients, the process I show here, is performed using the code that is which is also used in how we obtain the table. This is the Python script. Get CIJ tensor. And let me see the options. String 0.005 in our case, and volume 110. This will give you the elastic coefficients which we have. Then this is 1,1, this is 1,2, this is 1,3, and this is the C14. This is not significant, but these are actually numerical inaccuracies because we use a smaller K points and also a smaller wave cut energy. But this should be 0, but we have the one C44 here. C44 because we apply the E4 string. Okay. So using this is the tensor for the wave 110 volume. I haven't shown you the output for the elasticity calculation. So after that, we will have input, output, and arrow, and this result showing that the calculations is done or the convergence is finished. And after that, we okay here. So the elastic coefficient for this volume is stored in the Cij.data, and this is the file I just show you using the code earlier to obtain the Cij tensor from that code. So let me see how we do KeyNet. I think the time-consuming part is just a quantum espresso calculation, but we can go to the okay, you can see on KeyNet, this is I have run previously, the elastic parameter the equation of state parameters. And I also have I can do the same thing. For example, as this. Just copy the command. This will, because I believe this volume equals 110 is finished, I can just use the same code. Oh, I haven't installed this package. Oh. This will give you the same thing as what we have earlier. Let me see what I have finished. I have finished up to 140, so I can I will try to comment out the volumes I didn't finish. Okay, so here I specify the volumes I need to do on the equation of state and elastic coefficient, and the string and the percentage of stretch or compression I need to apply. And I think I will be able to do the same thing to obtain the elastic coefficients for the finished configurations. So this is the new equation of states, and yes, because I only finished 4 volumes, and there are only 4 volumes here, and you can see in the elasticity data, there are only like 4 different volumes here. This is the pressure volume and corresponding elastic coefficients, and these are the lattice parameters. So I guess if you want to try this, you will be able to. And this is the elastic coefficient as a function of pressure. I guess that is all I want to share today. And this instruction are contained also in this folder. I don't know how I can share the code for KeyNet, but I will try to make a archive of them. There will be slightly change in the JavaScript if you use KeyNet, but that's all. Thank you. Thank you for your patience.
Chenxing, can you hear me?
Mm-hmm.
So
yeah.
Thank you very much. Okay. Maybe you could write some of those commands that you run either on Expanse or on KeyNet on the hackmd, like key and like chi, sorry, and maybe you can share with us later. Not now, but maybe later.
Yeah, sure.
But otherwise, thank you very much.
Yeah, no problem.
So thank you so much. Now, are there questions? So no questions right now.
Mhm.
I think questions will come when we also try to run stuff. Sure. A lot of stuff coming.
Okay, so questions will follow after some time when people have opportunity to practice more.
Okay, no problem.
So thank you very much, Chenxing.
Yeah, sure. Yeah, sure, no problem.
All right. I think this was the last thing on the schedule today. So we can have some minutes breaks unless Renata is going to address also, she's going to revisit the talk where she was talking about the thermoelastic properties of the earth. So there was the idea she talked in 30 minutes, but let's wait and see. But I think there's probably more. So I found it especially interesting. What completely theological concepts for us to do is that's the kind of place where you pick up ideas that you can work on. So if there is more to hear about this, I would encourage you strongly to listen and to
Say hi to him. Hi, Chenxing. Thank you so much.
Yeah, no problem.
Very, very much appreciated. Okay.
Thank you.
You probably didn't see it last time. It's there. 9:30, even there now. Yeah. But very nasty. We are done for today. Tomorrow another student will come up and we will talk about home class party and I can follow dispersions and what we do with them. Like unharmonic thermodynamics, this one to show an example that we calculated recently of phase boundary, completely unharmonic phase boundaries, and the thermoconductivity. So, yeah, so that's essentially tomorrow. So I think we are done for today. Thank you.
Okay, bye. See you. I'm leaving.
You're still there. Okay, thank you.
Yeah, no, I was listening. I was listening to the seminar. Bye.
see.
See you.
Okay, bye. See you tomorrow.
Bye. Ciao.
See you tomorrow, right?
Yeah. Okay. See you in the sense that we will. Yes, I will be. I will be there. I will try to be with you also tomorrow.
Okay.
Ciao. Bye. See you. Ciao. Sorry, I have the camera off. That.
Okay, I'm going to end this session. Okay, Chenxing?
Yeah, sure. See you.